Welcome to the background lecture on the sustainable use of materials. This lecture is based on a plenary talk I gave at the SAM19 conference in Spain earlier this year. The corridor for material use is based on the notion that materials are limited. So let's see what we know about human material use and its limits. If we look into history, we see very distinct pattern of humans' material and energy use. We can take the big cultural division of mankind in history, the hunter-gatherers, the agrarian society, and the industrial society, and not only were these regimes different in their culture, they were also different in their energy and material metabolism. In particular, at each human development stage, the material and energy use increased by a factor of 4 to 5. So today, in the industrial society, we have larger than ever per capita material and energy flows. And these drive major environmental impacts, which we're going to have a look at in a moment. Materials are not directly included in the UN SDGs, but indirectly they are. The water goal is linked to water, of course. Energy is linked to energy and materials. Poverty is linked to food and thus also to materials. Decent work and economic growth needs materials to work with. There needs to be industrial production. The same with innovation and infrastructure, also linked to materials. Cities, goal number 11, are linked to materials. Consumption and production linked to materials, the stuff that the products are made of. Climate action, life below water, life on land are all driven by material production, which we will see in a minute. Another question about materials is, are there enough materials? So there is this spectrum from being totally relaxed about the geophysical availability of materials to panicking because we might run short of something. And here it is crucial to understand that there has been a major paradigm shift in the last year regarding the availability of materials for human use. For example, as we have better surveying, better estimation, and better drilling for material samples, we learn that in principle there's a lot of more materials accessible at different places than we previously thought. So the boundary between resources and non-resources, so in principle economic resources that can be mined, shifts as mining technology develops and surveying expands across the globe. And we have as massive degrees in copper ore grades, for example, so we mine lower and lower grade ores, but this is possible because of the innovation that was done to make these huge supplies of low grade ores available by grinding them, for example, by building the infrastructure. And this means overall, the question of resource shortage shifted to a question of the many resources we have, what is actually economic to recover, what is socially acceptable, and what is environmentally feasible. So we have enough stuff. It's not a major issue of geophysical constraint, it's more an issue of economic, environmental, and social constraints, so about a sustainability constraint. Having said that, there may be actual physical constraints for the large quantity materials, that is the concrete suitable sand, and of course we know that we don't have enough wood and biomass than we could potentially use. Also, some very few technology metals like rhenium are actually supply limited. The supply is not so much an availability problem, but a geopolitical problem. The resources are concentrated in certain countries that have certain trade regulations, that have maybe ambitions to control large parts of the markets, to exclude certain technologies or other countries from importing these materials, or they may be prone to conflict, or there may be a risk of conflicts, for example, in the Congo, or sometimes maybe also in South Africa. So it is a geopolitical problem as well. And we have these shifts in the geopolitical arena from the fossil fuel now to materials for renewable energy. So also there is a paradigm shift. And the idea is that the restriction of access to the material flows is now a growing concern also on the material arena, not just on the fossil fuel arena. Another major sustainability challenge to materials is their climate impact. So with the large quantities we produce, we can now say that around a fifth to a fourth of total global greenhouse gas emissions, man-made greenhouse gas emissions, come directly from our material production. And there, no vehicle drives, no building is heated. It's just producing the steel, the aluminum, the copper for making these products. So it's huge, and many of these emissions are costly to mitigate or difficult to mitigate because we yet have to develop some of the technologies like inert anodes in aluminum production, carbon capture and storage technologies in the cement industry, or certain hydrogen-based steelmaking technologies. Finally, there may be a waste and final sink problem. If you look at these huge quantities, 60 million tons of e-waste, 360 million tons of plastic waste, food waste, billion tons. So this sheer amount needs to be handled at some point. Also, there needs to be recycling and a safe storage of the residual waste. There's a problem with immediate toxicity. Think of leaching from landfills, for example, or marine pollution from runoffs. And there's another challenge related to permanence. Some organic pollutants, think of fluorinated organic components, they're persistent, they don't decompose, and they accumulate in living organisms, and this may lead to health risks in the future. Next to the geopolitical concern of metal sourcing or material sourcing, there's also the local impact problem. So this is the environmental and the social challenge related to future mining. Even though there are enough resources for most materials, many of these resources are located in biodiversity-rich natural biomes, making their mining, their exploitation particularly impactful and maybe thus prohibitive. Or say, speaking differently, many standards regarding mining and protected areas we have in the global north are not applied in the global south. They would not be scalable, right? It would not be acceptable in the global north, the kind of mining that happens in the global south to secure global resource access. And this means, as a summary, our metal-intensive lifestyle only works because environmental and social standards are low or ignored in many mining countries in the global north or also in Russia and China. So if the civil rights we have in the global north expand and the resource incentives lifestyles expand and the tolerance of mining decreases, the whole mining industry cannot continue to grow in this way. There is a lack of acceptance. So all of this leads us to think that there must be something like a corridor or here a donut. So there is a certain minimum requirement we need for a decent life, social requirements, a social foundation that translates into a certain reasonable or decent use of materials, but there are global caps linked to ecological ceilings, but also linked to social feasibility, ecological damage, and social acceptance in many biomes in the world where the mining happens. So this is a bit of the framework. And in our field, social metabolic research, we have a comprehensive analysis framework. So we really try to bridge the well-being aspect of sustainability with the ecological or climate and land use impact of sustainability by looking at this intermediate step in form of a material and energy service cascade. And it works as follows from left to right. So the well-being is promoted or supported by meeting our needs and benefits. For example, opportunity, safety, autonomy. These are aggregated benefits that are constituents of well-being. For these benefits, we need services. For autonomy, for example, we need enough living space. For opportunity, we need transport. And these services or these these services like transport are delivered by functioning, for example, a vehicle driving or a building service by a heated or cooled building. So the functions are represented by operating stocks. So from well-being to needs, from needs to certain functions, from needs to certain services, from services to products and buildings and infrastructure operating, which is the functions. Now the products and stocks, again, have to be built and operated. So at some point, there needs to be energy in the building for the heating, energy in the vehicle for the driving, but also material. At some point, the building needs to be built. So we have these build-up material flows and also energy for construction, and we have operational material and energy flow. And they are then on the right side linked to their respective supplying and producing and manufacturing industry, the energy supply sector. And these are then the sectors that are the major drivers of environmental impacts. And of course, we can recycle materials, so we have some material cycle here as well. So we have in this one big framework the social, environmental, and economic aspects of sustainability, with a focus, of course, from our field, social metabolic research, on the metabolism of energy material in the different stages in our economy. And we need these stages because all of them represent an opportunity for coupling or decoupling different products, different services, different benefits, different energy carriers, different materials. All of them can mean that the coupling between one stage in this cascade and the other one gets stronger or weaker. And the strategies we have, all the way from denser cities, that's more on the left, to low carbon energy, more on the right, all these strategies contribute and can be analyzed in this large overarching quantitative systems analysis framework. A particular focus in this framework is the circular economy. The circular economy is a vision for sustainable material cycles. In this famous butterfly diagram, for example, you see that instead of mining on top, manufacturing, using, and disposing of materials, we would try to close the loop and take the materials that we don't need in old products and other waste flows and try to cycle them back into useful materials. And we also try to do this separately for the biological nutrients, biomass, for example, food waste, because they are much easier to bring back into nature or extract from nature. And on the right side, the technical nutrients, the metals, the construction materials. The less these big cycles interfere, at least that's what the vision says, the better it is for the environment because of less dilution, less pollution, and so on. So the idea is we have a regenerative economy that regenerates biological resources and it keeps the products and components at high value at all time. So circular economy really means circular. The materials go in circles at high value. That's the economy side of things. So at high value, materials go in circles. The reality, unfortunately, doesn't look that optimistic. In this classic diagram by the Boku colleagues in Vienna, you see the global material flows and the recycling back. The four big categories are yellow, the fossil energy carriers. They're, of course, used for energy and dissipated. Biomass, mostly energy use, a little bit is material use. Short-lived products are paper and packaging, for example. And there's this big orange flow, these are all the construction materials, and there's these relatively small blue flows, these are all the metals. Huge driver of impacts, but in the overall quantity rather small. And you see two things here. First is the stocks continue to grow. So in this particular year, we added 26 billion tons of new construction materials and some metals and biomass to our cities, to the stocks, and only 9 were extracted from demolishing. So much more is added to stocks because of growing global urbanization than is removed or demolished from the stocks. And then out of these 9 billion tons of waste, only 4 were recycled. So the overall recycling efficiency is rather low. 4 out of 13, right? We have short-lived products and long-lived products all together forming the end-of-life waste. 13 billion tons of end-of-life waste, only 4 of them are recycled. And on the input side, because of the high throughput, we have 30 billion tons of new material use, of which only 4 come from recycling. So this is not circular. There is a circle, you can see it, but it's small compared to the linear throughput and to the stock accumulation. So we can quantify these indicators, the end-of-life recycling rate 4/13 and the recycling input rate 4/62. So if you use all materials, it's only 6%. And the future tells us that we need more of most materials because of technological development and also in particular of low carbon energy. We need more copper, more specialty materials for electronics, lithium for batteries, cobalt for batteries. And all this surge in future material demand will definitely not help in the first place to make the economy more circular, because we first have to expand the use stocks. Any stock expansion must come from external primary production. Recycling would only be possible in a later future. So given the sustainability challenges of metal supply and material supply, given the large quantities, we need to be broad in our thinking what sustainability strategies could include. This includes all stages of the energy service cascade, including lifestyles, including the question why we consume. Here you have a depiction here that is again massive growth in devices and so on. At the same time, we may have less time for individual hobbies or sports or other activities. So there is clearly a very strong coupling that a lot of life satisfaction today in the global north is achieved with high material and high energy throughput. So if we ask the question of why do we consume, we can discern different categories. Clearly, at the end of the spectrum are the basic needs, so essential consumption like basic food, basic shelter, and on the other hand, consumption that's clearly luxury. And in between, you have habitual consumption that we don't question, that are just engraved by us, by our cultures and norms, like regular meat consumption, for example, frequent leisure travel by car. At the same time, we have specific needs and wants that some people say they have to have their 3 vacation flights per year or something like that. But there's also the rebound goods, consumption that we never intended to have in the first place, but that we need to keep other lifestyle aspects in place. And the most famous or infamous example is commuting, of course. You want to keep your house and friends here, the job moves on, so you start commuting. So we can address basic needs by so-called decent living standards. So the amount of services, materials, and energy you need to have satisfactory life with your basic needs met. So this is the lower end of a possible consumption corridor. And then we need to ask ourselves how much of the consumption on top can we allow in a sustainability constrained world, and what is a healthy level of inequality here, because we don't want the same for everybody. We of course are individuals with individual preferences, and we can afford more than DLS, than different living standard. That is also possible, just not at these excessive levels as today. But still there is a question of what is possible in terms of healthy, prosperous consumption and its inequality beyond the DLS. And when we do this, we need to keep in mind that consumption doesn't mean throughput like food consumption. It also means building up the in-use stocks and using them for a long time. And these in-use stocks, the buildings, vehicle infrastructure, and all the appliances, they provide a service to us, but they also represent the capital containers where we put in our investments into cars, into buildings, for example. They are the resources for future urban mining. So we need to track them to make predictions for future recycling levels. Their lifetime determines the dynamics of the system. The lifetime of cars determines how fast we can phase in new technologies. The same with buildings. And these stocks are wealth indicators. They tell something about accumulated physical wealth of a region, a nation, or a certain population group. And these stocks, with their properties, determine how much energy I need to operate the stocks. The efficiency of the car determines how much energy I need for its driving. So the stocks, their properties, couple the consumption of energy to their operation. And finally, this physical or the spatial arrangement of the stocks shape the cities. Are the buildings residential and non-residential co-located, or are they segregated? That really has a major impact on the transport demand, for example. So we have to monitor the in-use stocks next to the material flows. And we conceptualize this by the core part of the energy material service cascade, which is the stock flow service nexus. And the idea here is again that the human well-being is in part determined by the services we consume, mobility, shelter, or communication. And these are, as we have just learned, mediated by the in-use stocks, the transportation by the vehicles and infrastructure, the shelter by the buildings, and so on. And again, as said before, these stocks need energy for building up and materials for building up and energy for the operation. And so the energy and material supply, the industry supplies the energy for driving the vehicles, but also the steel for making the cars. And all of these elements together form the stock flow service nexus, from services to stock, from stocks to energy material flows, and of course later to emissions. So let's have a look at where we stand in terms of stock expansion, the limit to the circular economy, and flows. So here we see a simple representation of the mass balance equation. Inflow is either stock change or outflow. That's what the mass balance says. Everything we consume either expands the stock or it compensates for outflow, for demolition. And you can plot the ratio of stock change over input to see the fraction of input that goes into stock change. And we have distinct pattern, clearly distinct pattern. We see that emerging economies, think of Egypt, for example, put 80% or more of their steel consumption into new cities, new infrastructure. They're expanding the stocks. Forget about circularity. They just grow their stocks. The economy of the maybe middle income countries, here you see Brazil, Mexico, Turkey as examples, they are declining over time. So they started maybe at 80, now they go down to 50 to 60%. So that means that the rest, the other 50%, the other 40%, they are maintenance. They replace outflows. Constant stocks means inflow replaces outflow. And then you have the high income countries, which are also the industrialized countries with mature stocks. You see this share goes down to 0%, close to 0%, meaning all inflow goes into maintaining, replacing outflow, no stock expansion, or for example, in the case of, I think it's Japan or Germany, even slightly negative, stocks are shrinking, more outflow than inflow. So you see the development stage, the maturity of the stocks determine how much stock expansion we have. If you have stock expansion, think back into this global economy Sankey diagram, you have no circularity. Another, actually quite depressing feature of our current material metabolism is the really short lifetime of our materials and our metals in particular. Here we have an own study, and the result shows that currently the average lifetime of copper in the technosphere, in the built environment, is less than 50 years. It's the red cross at the lower left corner in this plot. Because of improper collection of electronics, short lifetime, and improper recycling, we lose a lot of copper. And if the electronics only last for 3 years on average, and you have only a 80% recovery overall, in 30 years you have 10 life cycles, each time 20% loss. It accumulates so quickly. So overall, think about it. The environmental impacts of copper production will be there for millennia, but the use on copper in average less than 50 years, and then it's gone to landfills or other dissipation. So that's a major challenge. We need to come better at closing the loop, keeping materials in a circular economy at high quality. Another, next to improper sorting and collection, another hindrance for closing material cycles is the purity constraints for our secondary, for our recycled metals. Here it's shown for aluminium. So you see, if you want to have high yield strength, for example, what alloys are possible and which combinations are not feasible. So we need to be mindful of all these constraints to avoid the wrong chemical elements by contamination in the shredding and the sorting of waste streams entering these alloys for recycling, to really be able to also have high quality, especially high yield strength material from the recycling. And if we put all of this together, the different circular economy strategies, the avoid, shift, improve. So avoid means really different consumption patterns, less transport, less floor space by more intelligent city design, for example. If we have the shift, the modal shift, the energy carrier shift, and if we have the improvements, the efficiency and so on, we can start thinking about low carbon. So for example, here on the left side, you see a reference scenario for the global building stock where we see all these circular economy strategies together can save more than 40% of actually cumulative emissions. So that is quite impressive for cumulative emissions by 2050. So ambitious mitigation is possible with only circular economy, but we need all the circular economy spectrum, avoid, shift, and improve. And if you switch to the right side, you see here that even with a gray shade baseline, we can already in the building sector have reduction of emissions because of decarbonization of energy. That's possible, but it's not low carbon, it's just a bit less carbon. If you want to go low carbon, you need to switch to the red, the colorful, the red, orange, and blue strategies. So this is low carbon energy supply, right? They bring you to really low carbon emissions. And if you go really low carbon, you need the LEMD and SSP1 scenario. So these are the ones that have the avoid solution, less floor space, more compact housing. So really low carbon means you must combine the demand side solution, avoid strategies with the supply side solutions. So this brings us to a general outlook. With this background, we can start formulating what could be the constituents of a consumption corridor for the sustainable use of materials. The idea of consumption corridors means that we have a minimal requirement, so a necessary amount of material and energy consumption for people being able to live a good life. But we also have a maximum that should on average not be trespassed to keep our planetary boundaries intact. So this defines the corridor. Similar to the donut economy, the donut economy would be translated into the material corridor. The social requirements give the minimum material and energy consumption. The planetary boundaries give the maximum energy and material consumption. So we have a key component of social sustainability here, the consumption corridor. And once we have a corridor, so it means there is a lower limit and an upper limit, we need to think about the distribution. Who gets how much? Because the corridor could say we have on average only a certain range, but still within society there could be huge inequality. So we want to see how we can link inequality of material, energy use, product, service access to this consumption corridor concept. So in particular, this means if we look at materials and especially the stock flow service nexus, we need to broaden our inequality scope. So next to the established monetary inequality indicator, mostly income and wealth, we also need to look at something that we could call socio-metabolic inequality. Access to transport, access to floor space, access to appliances, ownership of appliances. All of these things also matter in our daily lives, both for our well-being and also, of course, for energy material consumption. So socio-metabolic inequality. We need to study it because inequality is a major challenge of our time. The inequality we know drives consumption, lowers the social mobility because people try to keep their status, and it really negatively impacts trust, safety, and well-being of people. So this is established from the social science and behavioral science literature. But this inequality now is not only to be seen in monetary terms, income and wealth, but also in physical terms. So we could define the social metabolic inequality as inequalities in the use of energy and material flows, access and ownership of assets, buildings, infrastructure, appliances, and consumption of services. So really inequality across the stock flow service nexus. Think about the cramped housing. So this is an aspect of inequality. This would be service provisioning and floor space, shelter and transport, but also infrastructure asset and also food material use. So everything we can quantify in physical units in the stock flow service nexus is an aspect of social metabolic inequality. And we can study this inequality in such a framework. Here we can say we have the stock flow service nexus combined with socio-technical provisioning factors, the arrangement, the access, the business models. This together forms the provisioning systems. And they then deliver the services, the functions, they contribute to well-being via the benefits. So the provisioning systems link then to the material cycle and to the global supply chain, to the environmental pressure, and the stock flow service nexus, the services, the functions, and the well-being aspects, they link to the consumption corridors related to the distribution of the services in society and also the discourse on desirable inequality levels. And if you contrast this bluish framework on the upper side with the currently prevailing green growth economy framework, you really see the striking difference. The whole, let's say, society side is proxied by GDP as a proxy for development, prosperity, everything, no inequality, no real well-being. And this whole richness of service functioning and in-use stocks is proxied by energy services. And on the provisioning system science, the description of stock flow service nexus is mostly limited to the operation of in-use stocks via final energy, and there's business models, regulations, and technology in there, but not the spatiality, the public access, or the ownership issues. Industry is detached as an separate end-use sector typically, so you see there's much less richness that we need to understand the link in the stock flow service nexus, in the cascade, and also the inequality. Examples of research on social metabolic inequality are emerging. So this is a quite interesting example from colleagues from Hong Kong, also from the industrial ecology community. So Apurva presented this work first at the SEM conference in Beijing in 2024. They developed a spatial inequity index for facility as access at the building level. So for Hong Kong, one can really see from the map how equally across the buildings, for example, access to waste management facilities is distributed versus access to elderly care on hospitals. So this is the first step of using high resolution map data to actually study inequality and access to public transport across buildings, across population, or access to hospitals and other public services. If you now look at the global picture, we also see that there is considerable inequality. On the left side, you see it for residential buildings as a Lorentz curve, both floor space, so the shelter aspect, but also energy, and on the right side for passenger vehicles. You see that for passenger vehicles, it's quite highly unequal, Gini coefficient about 0.6, which makes sense, right? Passenger vehicles is something that only a fraction of the global population has access to. And also energy and the vehicles themselves are more or less the same because the vehicle without energy doesn't help you much, so it's tightly coupled. The situation looks a bit different for buildings. First of all, the relatively low inequality in floor space stock, even though we have huge differences across countries. But overall, it's a basic need, right? So there's some level of floor space in all regions, but it's different for the final energy. It's similar to the transport. Here, the final energy is much more unequal than the building stock itself, meaning that many countries have building stock, but it's not heated or cooled. That is basically the answer. So the thermal comfort, final energy, much more unequally distributed than the shelter aspect of the stock, the square meters. What we can also do, this is research from our own group, we can take the different basic services, shelter, education, healthcare, collective services, the communication, mobility, nutrition, and translate them into the average material consumption we need and also the stocks we need. And on average for these different services, a decent living standard, so really the threshold beyond which you report a satisfactory life conditions, is roughly 6 tons of materials in a standard scenario per capita and year. And if you do it more efficiently, for example, less meat, a little bit less floor space or different transport modes, you end up on only 3 tons. If you're on a more inefficient side, more meat and more individual transport for decent living standards, you end up at 14 tons roughly. So this is the average personal material throughput, and also the stocks that we need to provide these different living standards are about 32 tons per person in infrastructure, buildings, and so on, appliances, plus another 11 tons in some industry, mining and so on, recycling industry, all allocated to provide it a single person with such a decent living standard. So this is also something we know. We kind of know already the lower bound of the consumption corridors. We know it from the decent living standard assessment. Now the question is, what could be the upper boundary? And here I want to present to you some fundamental insight into the inequality indicators. Essentially, there is a constraint, and it's published in a paper that I wrote about 2 years ago. And the constraint is that the lead indicators for inequality, the Gini, for poverty eradication, the decent living standards, and for personal growth, the GDP or the average per capita stock, they're not independent. They are linked by the following constraint equation. And I got this equation by understanding that if you're serious about a decent living standard, it means that the poorest person in a given population will have decent living standard. This defines the slope of the Lorentz curve, these red and black solid curves here in this plot. It defines the slope of the Lorentz curve on the left side. Right? Nobody is beyond decent living standards. So the first person goes from 0 to decent living standards, gives you the minimum slope of the curve. And from this constraint, you get this consumption model. We also, but this is less ambiguous, so to say, less unambiguous. We also can use this consumption model to say something about upper limits, potential upper limits. So this here is a constraint that you get if you assume that in the upper decile, so the top 10%, nobody in that decile should be above the average in this decile. So this decile should be just the average and nobody should have excessive luxury consumption beyond this average. And when you add this constraint, you get an upper limit in the consumption corridor, the MLS, the maximum living standard, again calculated from the Gini coefficient and some power laws, times the basic living standard. So it's possible to use a relatively simple consumption model to formulate consumption corridors. So we can then link maximum consumption to minimum consumption to inequality, and also in a second step link this to how much is actually possible given the planetary boundaries. So linking personal eudaimonic well-being to maximum consumption with under the society-wide accepted inequality level. So this is possible with such a model, and it does not only work in the model, it also works in actual scenarios. So here we have an inequality scenario for energy services by Millward Hopkins and Oswald. And it basically states if you factor in inequality in your scenarios, you can only do the demand side solution and go into the really low carbon arena if you reduce that inequality. Because, and this is what I showed with my consumption model, if you keep high inequality, a high Gini coefficient, if you reduce poverty, so you go to DLS on the right side, but you still have the inequality, the G, you drive up consumption. And this is what they showed in their scenarios. So really, the poverty eradication, decent living standards, and reduction of Gini coefficient must go hand in hand if you're serious about a low carbon future. So this is a major finding from the recent years of scenario assessment. So let me summarize and conclude. It's a stylized fact that 20 to 25% of global greenhouse gas are only from material production. And this massive material use only works because environmental and social standards hardly play a role in many mining countries. We have a glaring global inequality between the benefits and the damage from metal use, but also an inequality in the amount of stocks in our cities across countries. We also have a huge temporal inequality between the short benefit and lifespan of metals, just a few decades, and the millennia, thousands of years long impacts environmental damage elsewhere in the world and in the future. This means that our resource intensive lifestyle is not scalable. We cannot scale up global north, western countries, high income countries lifestyle to 8 or even 10 billion people on the planet, because for some materials we lack the supply, sand and wood in particular. For others, we have a greenhouse gas constraint that's hard to overcome, like for steel. And for many technology metals and also copper, we have this prohibitive mining damage that will at some point not be acceptable anymore, environmentally and socially. So we must go down with our primary production of materials if you're serious about sustainability related to materials and the climate targets in particular. This reduction can still deliver high well-being, but only if demand-side solutions are included, different transport patterns, compact cities, and so on, less meat in your diet, and the inequality distribution is addressed in a consumption corridor. That means for circular economy, right, so doing things in circles to save resources and the climate, we must include the narrow strategies, the sufficiency, lifestyle, urban form strategies, building design strategies in the spectrum of circular economy strategies. We need a systematic approach to address, to find ways to have less primary material production. All the measures need to come together. Product design for less material use, building regulations, different alloys for easier recycling and mixing, better waste management. So this is really a clear demand from our research that this needs to happen if you're serious about sustainability, both intra and intergenerational. The sufficiency solution, that's the good news, is directly related to urban and rural lifestyles, and we need respective infrastructure, supporting infrastructure and provisioning system to enable sufficiency. It's not about individual choice saying no, it's about providing better alternatives, providing better infrastructure, different buildings, different transport, different food products. And that means also that this contraction and convergence paradigm of climate protection, which apply to emission, also should apply to metal stocks in use. If you're serious about global sustainability, also the in-use stocks of stuff need to contract at lower levels than we see currently in high-income countries, and they need to converge within societies and across countries. We can also distill a lot of research needs from that. We need better data to assess the contribution of inequality to inequality of the different physical stocks and flows, and also to human well-being. Simply overlay the inequality of housing space with reported well-being, for example. We have some high-resolution data that we can use here. We need to identify physical well-being measure beyond economic or purely subjective ones. Service provisions rather than material stocks should be included. And we need a debate on desirable levels of inequality and link it to material related core indicators, for example, via consumption corridors for materials by economies or cities, the minimum standard we need for a good life and the maximum standard to respect global boundaries. And that in particular means that there needs to be a talk and a debate at some point about upper limits to consumption in different contexts. So we should sit down at some point, define thresholds for excessive consumption that's not tolerable in a sustainability and resource constrained world, and also identify suitable policy measures to address that. So this was quite comprehensive. I hope you found some interesting aspects in here. I want to thank you for your interest and attention and point you finally to our open science portal at industrialecology.uni-freiburg.de. We have a database, we have visualization tools, guidelines and standards, software, more material, including teaching material, and our blog where we deep dive into some of the aspects here. Thank you for listening.